Welcome to the afternoon session of the last edition of Modules and Whatnot. Our next speaker is Tariq Syed, who will talk about the cancellation of projective modules of rank 2 with a trivial determinant. And everyone feel welcome to ask questions during the talk by unmuting yourself and asking the questions. And please be muted when you're not asking the question. Thank you.
Yeah, first of all, thank you for the invitation to give this talk. As you said, I will talk about the cancellation of projective modules of rank 2 with a trivial determinant. So I will start with a brief survey on the cancellation problem in general for projective modules or algebraic vector bundles. The main part will be, as I said, the cancellation of projective modules of rank 2 with a trivial determinant. I will introduce the Vaserstein symbol as defined by Susin and Vaserstein, and then I will talk about my work on the generalized Waserstein symbol and talk about some applications, and towards the end I will discuss some applications to the generalized Serre question. Okay, let's start. R will be a commutative ring with unit, and P will be a finitely generated projective R module, basically always in the talk. So the question is, does a stable isomorphism, so does an isomorphism between P plus R to the n and Q plus R to the n for some Q and some n already imply that P is isomorphic to Q? So in a way, if the class of P and Q and K0 are equal, are they already isomorphic? And such a projective module is said to be cancellative if any such isomorphism, any such stable isomorphism already implies that P is isomorphic to Q. Okay. So let me rephrase this problem. So first of all, we denote by VR the set of isomorphism classes of finitely generated projective R modules of constant rank R, where R is any non-negative integer. And we consider the stabilization maps from vector bundles of rank R to vector bundles or projective modules, sorry, of rank R plus 1, sending any class of a projective module to the class of P plus R. So we simply add the trivial line bundle. And the main goal is to describe the fibers of this form, the fibers of these stabilization maps. And there's a canonical way to describe them, as I will show you now. So we fix such a finitely generated projective R module, as always, of rank R, and we denote by P plus R the set of epimorphisms, of R linear epimorphisms from P plus R onto R, and by aut P plus R the group of automorphisms, R linear automorphisms of P plus R, which is acting, this group is acting on the right on the set of epimorphisms just by precomposition. And maybe a little bit easier the case when P is a free module, so we can identify this set of epimorphisms from R to the R plus 1 onto R, and this group aut R to the R plus 1 with the usual sets of unimodular rows of length R plus 1 over R, that is just, row vectors of length R plus 1, whose coefficients are elements of R, and which generates R as an ideal. That just means that the row vector defines an epimorphism. That's easy, I guess. And we can identify this automorphism group simply with GL R plus 1, the group of invertible matrices of rank R plus 1 over R. And then the right action that I mentioned above is simply given by, of course, simply given by matrix multiplication. And then there's a very simple description. So this fiber that we are interested in of the stabilization map is simply given by the orbit space of this set of epimorphisms from P plus R onto R modulo the right action of the automorphism group. And well, this identification comes as follows. If we take an epimorphism from P plus R onto R, then this is necessarily split, so the kernel is a finitely generated projective of rank R, stably isomorphic to P plus R, to P, and hence defines an element in the fiber. So we simply send this epimorphism to the kernel, to the class of the kernel of it, And conversely, if we have a stable isomorphism, we simply take the class of Q and send it to the composite of this isomorphism and the projection onto R. And this is, as one can check easily, this is simply an identification of this orbit space with this fiber. And this is what one is actually interested in, studying these orbit spaces and trying to somehow describe them, further describe them, and maybe prove that they are trivial. And yeah, just as an illustration, if P is free, we can of course simply use this above identification and get an identification on this fiber. And this is just the orbit space of unimodular rows of length r+1 modulo the right action of invertible matrices of rank r+1. And that this orbit space is trivial just means that every unimodular row is the first row or the second or third, the first row, for instance, of an invertible matrix. So basically it's that means that every unimodular row can be completed to an invertible matrix. Okay.
Sorry, can you please say again, what was VR?
VR was the set of isomorphism classes of projective modules of rank R. So if you think of affine schemes instead of commutative rings, just the set of isomorphism classes of vector bundles of rank R.
Yeah, Tariq, I asked about VR, the homomorphism.
Sorry?
That's right.
Phi R. Phi R is the stabilization map. This one.
Okay, cool. Yeah.
And this
great.
is so we're rephrasing this cancellation question in terms of this stabilization map. So a projective module P is cancellative if this fiber, for instance, is trivial. So if this map is injective, all the projective modules of rank R are cancellative. That's what I'm trying to describe. So we have this description in terms of this orbit space, or in case P is free of this orbit space. And now I wanted to start with this actual survey of results on this. So now we have a commutative ring again with unit as always, and now it's of cruel dimension D. D will denote the dimension. And P will be a finitely generated projective R module as usual, now of constant rank R. And then basically if the rank is large and is big enough compared to the dimension of the ring, then P is cancellative. So Bas proved in 1968 that if R is at least D+1 and R is unitarian, then P is cancellative by introducing his stable range conditions and so on. And in 1977, and by the way, I should say that this is the best result one can prove in this generality. There's no improvement, simply not possible because of a counterexample, the real algebraic two-sphere, but I'm not going to discuss this in detail, just a brief survey. So focusing on affine algebras over algebraically closed fields, Suzin proved in 1977 that if R is equal to D and R is an affine algebra over an algebraically closed field, then P is again cancellative, and this was slightly improved by Badvadeka in 2003.
Sorry, can you say what you mean by affine algebra?
Oh, sorry. Yeah, affine algebra just means finitely generated algebra.
Okay, so why is the sphere not a counterexample for this?
The real, you mean the real algebraic two-sphere? Because the tangent bundle is of rank. It's stably free, but not free. One can use this.
Why is it not a counterexample to this result of Suslin? If you take it,
because the real algebraic two-sphere is over the real numbers. It's a smooth affine algebra of dimension 2 over the real numbers, but not over the complex numbers, for instance. So.
Oh, you're saying that over C that module is free.
Yes.
Okay, I see. Thank you.
So you really use that you're having a algebraically closed base field. So I chose, maybe I should say this, I chose the language of commutative algebra because the definition of the generalized Waserstein symbol is much easier in this language. but you can always think of affine schemes and just algebraic vector bundles of rank R in each step. And affine algebra just means a finite type over the base field, and yeah. But Vadeka improved this result a little bit. So he proved that if R is an affine algebra, a finitely generated algebra of an infinite perfect field K of cohomological dimension at most 1, and D factorial is a unit, then P is cancellative. So up to some further characteristic assumptions, he extended Suslin's result to a base field of cohomological dimension at most 1. Okay. Then in 2011, Fasel proved that if R is a smooth affine algebra of dimension 3 of an algebraically closed field with characteristic different from 2, then at least R2 is cancellative. That is, stably free modules of rank 2 are free. So this was the first case in which the rank of the module, in this case 2, is D minus 1, and not just D or at least D plus 1. And it's a special case when P is free, basically. And I want to sketch the proof because this is the motivation of all my work, basically, on the generalized Waserstein symbol. So first of all, if we have a stable isomorphism, we can already use Suslin's cancellation theorem to deduce that at least this isomorphism should be, we have an isomorphism of this form because R3 is cancellative. Now Q represents an element in the fiber of the stabilization map of R3. So we have to show that this fiber is trivial, or in other words, that this orbit space is trivial. And now we use a map called the Vaserstein symbol that I'm going to introduce later. It's a map defined on this orbit space, where now we have the right action of the subgroup of GL3 generated by elementary matrices. And on the right-hand side, we have the so-called elementary symplectic Witt group, which is, well, some sort of a reduced higher Grothendieck Witt group to some degree. Yeah, I think you can say that. And Rao van der Kahlen proved that this Vaserstein symbol map that I will introduce later is a bijection, and hence induces a group structure. On the right-hand side, the object is an abelian group. It's a higher Grothendieck Witt group. So this induces a group structure on this orbit space of unimodular rows modulo the right action of elementary matrices. And this Vaserstein symbol has some nice properties. Namely, there are certain formulas. So the n-fold sum of such a Vaserstein symbol of some row, B1, B2, B3, of length 3, is just given by the row where we take the n-fold power for the third coefficient. That will be useful, and we will see that in a minute. And as I said, this elementary symplectic Witt group is actually a higher Grothendieck Witt group, and can be computed by using the Gersten-Grothendieck Witt spectral sequence. And one can prove that this is actually 2-divisible. That's another property that we are going to use. And there's a well-known theorem by Swan and Tauber, who proved that any unimodular row, so any row vector of length 3 of this form, where the third coefficient is a square, can be completed to an invertible matrix of rank 3 with determinant 1. So let's put this all together and prove this theorem. So we start with any unimodular row. And now we know this is a bijection. So we immediately see that because the Vaserstein symbol is a bijection, this row can be transformed via elementary matrices to some, yeah, well, we have a group structure on this orbit space. So 2 times something, because this group WE of R is 2-divisible. 2 times some row that we don't know anything about. But now this first formula shows us that 2 times something is just the same row where we take the square in the last coefficient. So up to elementary transformations, we have this, we get this row. And now we use the theorem by Swan and Tauber, which asserts that any such row is the first row of an invertible matrix of rank 3 with determinant 1. So any row can be transformed via invertible matrices to the standard unimodular row 1, 0, 0. And therefore, this orbit space is trivial, which corresponds to the fiber of the stabilization map, and hence the cancellation theorem, this one, is proven. So the ingredients is basically the Vaserstein symbol, properties of the Vaserstein symbol, for instance, the bijectivity and that it induces a group structure, and the fact that this group on the right-hand side is a higher Grothendieck-Witt group and hence computable by using the Gersten-Grothendieck-Witt spectral sequence. Okay.
I have a question.
Yeah.
For your second point, GW13, what's the red there?
Red, reduced,
Yeah.
because we take the, well, I will explain that later maybe. I will introduce this group, and then I can tell you what reduced means in this context. Okay.
And in the first point, n times v b1 b2 b3, the raised to the power n on the right, it can be at any, for example, on b1 to the power n instead of b3.
Where?
So, I mean, for the first point, v n times v b1 b2 b3 equals v of b1 b2 b3 to the power n. The power n can be at any point, at b2, for example.
Yeah, actually, I didn't say that. Yeah, but we don't have to take the third coefficient. We can take any coefficient.
Okay, thank you.
Yeah, it's not that important, but I wanted to make this compatible with the Swan-Tauber theorem. So yeah, the twofold sum of any row is just taking the square at some point somewhere.
Okay, thanks.
Yeah. Okay. And then later in 2012, this result was extended to, well, all dimensions in a way. So the idea was exactly the same. So if R is a normal affine algebra of dimension at least 4 of an algebraically closed field, such that d-1 factorial is a unit, it's just a characteristic assumption, then the stably free module of rank d-1 is cancellative. That is, stably free modules of rank d-1 are free. And I said it's basically an extension of Fazel's proof, Fazel's ideas. So one starts with a unimodular row of length d now, because we take the stabilization map of R. Well, we want to study the fiber of RD. And now one proves very analogously using the Vaserstein symbol that one can transform such a row via elementary matrices to a row where the last coefficient or any coefficient is a d-1 factorial fold power. And then one uses not the Swan-Tauber theorem, but Suslin's famous n factorial theorem, which is the generalization, which asserts that any such row can be completed to an invertible matrix of determinant 1. So this basically shows that any row can be transformed to the standard unimodular row. In other words, every unimodular row is the first row of an invertible matrix of determinant 1. So this is a very similar proof, but I'm not going to discuss the details. And in 2014, it was actually the theorem by Fazel was for three-folds was generalized, extended to every projective R module. So if R is a smooth affine threefold of an algebraically closed field K, whose characteristic is different from 2, then any projective R module of rank 2 is cancellative. Not just the free module as proven by Fazel, but actually every projective R module of rank 2 is cancellative. And this followed, this was implied by a complete classification of rank 2 bundles, of projective modules of rank 2. So Ashok Fazel proved that the Chern class map, assigning each projective module its first and second. What? Assigning to each projective module its first and second Chern class is a bijection. And hence, if modules are stably modules of rank 2 are stably isomorphic, they have the same Chern classes, and hence they already have to be isomorphic. So this easily implies cancellation in this case. And one would like to go further. So this is the case d minus 1, r is equal to d minus 1. One would like to say something about the case r is equal to d minus 2. But in this case, cancellation has been disproven. So for any algebraically closed field K, Moore and Kumar constructed an example of a smooth affine K algebra of dimension 4 with a non-free, stably free R modulo of rank 2. So the cancellation of projective modules of rank 2 in dimension 4 is a particularly complicated or subtle problem. So the question, the motivating question for this talk is, let R be a unitarian ring of dimension 4 and P a projective module of rank 2, preferably with a trivial determinant. Is there a criterion, preferably a cohomological criterion for P to be cancellative or not? And the approach is motivated by Fazel's proof for threefolds. So define a generalized Waserstein symbol, which will then be defined on this orbit space, P plus R modulo EP plus R, where EP plus R is just the subgroup of the automorphism group generated by so-called elementary transvections, which are the perfect generalization of elementary matrices. So in case P is free, we just get 3R modulo E3R as before, and it will map into a group denoted V tilde of R, which is canonically isomorphic to this elementary symplectic Witt group that I mentioned earlier, but I will introduce this now. And it will be associated to any projective module of rank 2 with a fixed isomorphism from R to its determinant. So basically, we always assume that P has a trivial determinant in this talk. Okay. So let's start with this. First of all, let's define this group WE of R, this elementary symplectic Witt group. So let R be a commutative ring with unit, as always. And for any n, we let A2n denote the set of alternating invertible matrices of rank 2n. And then we just inductively define an element psi2n in A2n by setting, well, first of all, psi2 is just this hyperbolic alternating form. And then we just take the block sums to get psi2n plus 2 inductively. And therefore, we have embeddings from A2m to A2n for m smaller than n, simply by adding psi2n minus 2m. And we can form the direct limit of these sets, A2n, with respect to all these embeddings. So basically, it's just all the alternating non-degenerate or alternating invertible matrices of rank 2n for any n. The disjoint union, the union, if you want, the direct limit. And now we define a relation on this set. So let G be either the direct limit of all the groups of elementary matrices, or SL of R, the co-limit of all the SLNR groups, the groups of invertible matrices of determinant 1.
May I ask you, so what do you mean by alternating?
Alternating means, well, if 2 is invertible, it's the same as Q symmetric. Okay. If 2 is not invertible, alternating means that, where do we have one? Well, phi of, if you think of alternating forms, phi of x comma x is 0 for every x. So if you have a bilinear form, the bilinear form is alternating if phi of x comma x is 0 for all x. And you can, yeah, this, the notion of an alternating matrix is completely analogous. Yeah. Okay, now we define a relation on this set AR. G will either be the direct limit of all these groups En generated by elementary matrices, or the direct limit of all these groups SLN, the groups of invertible matrices of determinant 1. And we say that M and N are G equivalent, and the notation is this: if there's an integer S and a matrix of the, well, the rank 2n plus 2m plus 2s of determinant 1 and in G, such that up to adding this psi 2n plus 2s or 2m plus 2s, these alternating matrices are isometric in a way. And in the first case, when G is ER, this just means E is stably elementary. So we have an isometry between these forms. I always think of alternating matrices as forms. We have an isometry given by a stably elementary matrix in a way. And in the second case, when G is SL, this just means we have an isometry given by a matrix of determinant 1. So one can check that this relation is an equivalence relation, and we denote the corresponding sets by WE prime of R and WSL prime of R, respectively. And some non-trivial fact, the operation taking the block sum of matrices equips these sets with the structure of an abelian group. So maybe quite immediate, one can actually see quite immediately that it's an abelian monoid, but one has to construct inverses. And just to make this brief, so if M is of rank 4M, not of rank 2M, but 4M, and we can always assume this by adding psi to M, for instance. So it's, if the rank is divisible by 4, then the inverse in these groups, is just given by the inverse matrix. So in this case, it's very easy. But in general, one has to enlarge M, the rank of M, until you have a rank divisible by 4, and then you have to take the inverse matrix. But yeah, this is something not entirely trivial. So it's an abelian group. We have two abelian groups now. And now we have a Pfaffian, a so-called Pfaffian on alternating invertible matrices. So for any M, we have a Pfaffian, which is a unit in R. Roughly speaking, is a square root of the determinant of M. So M is invertible, has its determinant is a unit, and its Pfaffian is a square root of the determinant. And it's compatible with block sums. It's compatible with isometries. So you always have to multiply the Pfaffian of N by the determinant of this isometry, if you think of G as an isometry between alternating forms. And the Pfaffian of this psi 2n is always 1. And this is enough to conclude that the Pfaffian defines a group homomorphism from WE prime of R onto the units of R, and analogously from WSL prime of R onto R prime, the units of R. And the kernel of these homomorphisms is then WE of R and WSL of R, respectively. So it's basically the same group as before. If you look at the construction, we have these direct limit AR of all these alternating matrices. So we could have just chosen the subsets of alternating matrices of determinant, of Pfaffian 1. And we could have defined the same relation and immediately could have defined WE and WSL by the same definition, just taking the subset of alternating matrices at each time of Pfaffian 1. But I think it was the question what the reduced higher Grothendieck Witt group means. So this WE prime is actually a higher Grothendieck Witt group. It's GW13. If you are familiar with Hermitian K-theory, that's GW13. And since we take the kernel under this Pfaffian map, I call this a reduced higher Grothendieck Witt group. Yeah, this WE of R is hence reduced higher Grothendieck Witt group. And now we can define the Vaserstein symbol. So let's pick a unimodular row of length 3 with coefficients A1, A2, A3. So since it's a unimodular row, we may choose B1, B2, and B3, such that, yeah, basically a section to the epimorphism, such that this equation holds, such that this sum is 1. And then there's a canonical associated alternating matrix. Yeah, just defined like this. It's obviously skew symmetric. The diagonal entries are 0, so that's actually enough to conclude that it is alternating. And the Pfaffian, there's a very concrete formula for the Pfaffian of such a matrix, and the Pfaffian is just this sum. So by choice of these coefficients B1, B2, B3, the Pfaffian is 1. And one can check, it's something one has to prove, but one can check that the class of this matrix in WE prime does not depend on the choice of these coefficients B1, B2, B3. So it only depends on A. So we obtain well-defined Vaserstein symbols defined on these orbit spaces, which map into this group WE of R, because it has Pfaffian 1, this form, so it goes into WER, and completely analogously into WSL of R. The only thing one has to check then is that it's actually well-defined on this orbit space. It's compatible with the actions of E3 and SL3 at each step, but that's very easy. Okay, so that's the Vaserstein symbol. Usually one calls this map the Vaserstein symbol, sometimes also this, but I think this is the original Vaserstein symbol as defined by Suslin and Vaserstein. Yeah, so this is the Vaserstein symbol. This is the map I wanted to generalize, but unfortunately I couldn't really, I mean, I could have, but it would have been very messy to use this group. So I used another group. I used the group which is canonically isomorphic, as we will see, but has a nicer presentation for at least for a generalization at least. So R is a commutative ring. Now we consider something completely different. We consider triples, where P is projective, finally generated projective, and G and F are now non-degenerate alternating forms. Yeah, now we have forms, not just matrices, we have forms. And two such triples are called isometric if there's an isometry or there's an isomorphism from P to P prime, which is simultaneously an isometry between F0 and F0 prime and F1 and F1 prime. And then we note by PGF the isometry class of such a triple. Now, the group VR is then the quotient of the free abelian group on such isometry classes of triples modulo some relations. First of all, it's compatible with the orthogonal sum of alternating forms, of non-degenerate alternating forms. And there's a second relation, which is just, yeah, P F0 F1 plus P F1 F2 is P F0 F2. So maybe an aside on that, you should think of these forms as a formal difference of alternating forms. So you should think of this triple as F1 minus F0, for instance. And then it's clear that F1 minus F0 and F2 minus F1 should be F2 minus F0. So that's what this relation tells us.
Is this supposed to represent the kernel of the map from GW alternating to K theory?
No, I don't think so. It's I mean, if you're familiar with Hermitian K theory, this is basically Karoubi's V group. That's the reason for the notation.
Oh, I see. Oh, and that's related by the Longirac sequence. I see.
Yeah. I mean, we will use the Karoubi periodicity sequence later. Yeah, this is just a presentation that is more accessible to the generalization of the Vaserstein symbol. So now we have an assignment, a canonical one, so we can consider any matrix alternating of rank 2n an alternating form, a non-degenerate alternating form on R2n, and we simply consider the triple R2n, psi2n, and m, which makes sense because we think of this as a formal difference. So m minus psi2n should be, I mean, psi2n is the neutral element in WE prime. So it should just be m. So this map is clearly, as one checks, well-defined, and it's not too hard to prove that this is an isomorphism. So we actually have just given a new presentation of this group WE prime. And then, of course, we can just take the subgroup that I call V tilde of R, corresponding to this kernel of the Pfaffian homomorphism, just corresponding to WE of R. Okay, so this is the group that I will use.
Tariq?
Yeah?
Could you please show for a second the previous slide? Okay, thank you.
Any questions or?
No, just trying to keep all the definitions in.
Okay, sorry.
Inside the head, thank you.
So we have just triples of non-degenerate alternating forms on projective modules now. So that's just a different presentation. Sorry for all the definitions. It's just a different presentation of this group WE of R.
So these are what's usually called formations, right?
I think so, yes. Yeah. Oh, wait. I think so, yeah. I'm not too sure, to be honest.
Maybe formations is only when one of the two is the hyperbolic. I don't know, but anyway.
Yeah, yeah. Something like, yeah, I think, yeah.
They're
something
clear.
like that.
but you can always generate with hyperbolics because, okay.
So completely analogously, yeah, don't read all the definitions. So this group VSL, so we want just to make the analogous construction for WSL now. We have found a new presentation for WE. Now we have a different presentation for WSL. The same definition as before. We take the free abelian group on isometry classes of triples as before, modulo the same relations as before, and now there's a third relation. We simply have this relation. So PGF is PG, and then the isometry, any isometry induced by an automorphism of determinant 1 should be the same element. So that's the relation, just to make this isomorphism from the previous slide still well defined on the when we go modulo SL, basically. So the same assignment induces an isomorphism, and we have a Pfaffian homomorphism. So again, we denote by V tilde SL of R, the subgroup corresponding to the kernel of the Pfaffian homomorphism. So yeah, we have just given a new presentation of WSL. So basically, forget all the definitions. We just have triples, isometry classes of triples of alternating non-degenerate alternating forms on projective modules now. Okay, so now we want to define the generalized Waserstein symbol. So we let P be a projective R module of rank 2 as always, with a fixed trivialization of its determinant. So we have such an isomorphism between R and the determinant of P. And this already defines a very canonical non-degenerate alternating form simply by, well, mapping PQ to the inverse of the wedge product of P. I mean, in the second exterior power, so the determinant. Yeah, we have a canonical non-degenerate alternating form, basically by assumption. So now we want to define the generalized Waserstein symbol associated to any epimorphism. So any element, because maybe I go one slide forward. So we want to define something like this and this. So we start with epimorphisms. So let's go back. So any epimorphism from P plus R to R gives rise to an exact sequence, which is necessarily split. So we consider this kernel PA associated to A, it's just the kernel of A. And any section, we have to choose a section here, determines a stable isomorphism from P plus R to PA plus R. And this isomorphism already induces an isomorphism on the determinant. So the determinant of P is then automatically isomorphic to the determinant of PA. And then we get another alternating form, theta A. So first of all, an isomorphism, theta A from R to the determinant of PA, just by composing with the isomorphism induced by the stable isomorphism and the original isomorphism from R. So I called it theta from R to the determinant of P. Okay, just by composing. And then completely analogously, we get an non-degenerate alternating form on PA using the same definition as before. And now we want to compare, in a way, chi A. I call this non-degenerate alternating form chi A. And on the previous slide, I defined chi. We simply want to compare these alternating forms in a way. So we define the generalized Waserstein symbols associated to P and this fixed trivialization theta, this isomorphism from R to the determinant of P, which are defined on these orbit spaces, which go to this group V tilde of R, and a second one on this orbit space, which will map to V tilde as L of R. And then we consider the formal difference. So we consider P plus R2. We can consider chi and the orthogonal sum with psi2, which is a matrix, alternating matrix on R2, and then hence we can interpret it as an alternating form, and non-degenerate alternating form on R2. So we can take the sum, and analogously we have chi A plus psi2, which is defined on PA plus R2, and now we simply take the isometry induced by the stable isomorphism. So I was defined on P plus R and is an isomorphism between P plus R and PA plus R, and plus the identity, or plus one, we get an alternating form on P plus R2. So philosophically speaking, we simply consider the formal difference between these alternating forms and somehow try to develop an understanding for cancellation by means of this assignment. So that's the generalized Waserstein symbol. One has, of course, to check that it really maps into the tilde of R. So basically, under the Pfaffian homomorphism, it goes to 1. Similarly here. And one has to check that it is compatible with this action of transvection groups. So this was the generalization of elementary matrices, and SLP plus R, which is the generalization of matrices of rank of determinant 1. So one has to check that all this is compatible, but this is not too hard, and one gets well-defined Waserstein, generalized Waserstein symbols with this assignment. And yeah, this is the definition. And now I would like to discuss applications. But first of all, I should maybe say one thing about the connection with the usual Waserstein symbol. So if we take P equal to R2, so P is free, then we have a standard basis on R2. That's, I guess, well known. And then we have a canonical isomorphism induced by this basis, sending 1 to this standard basis of the determinant of R2. And this is a canonical trivialization of the determinant of R2. And unfortunately, the Waserstein symbol associated to R2 and this trivialization is not the usual one, but one can somehow modify it, and one has, in fact, simply you have to take minus this isomorphism, which is still an isomorphism. So 1 goes to minus this basis. And then up to the isomorphism between Witt tilde and WE of R, you obtain the usual Waserstein symbol. Why is this the case? Well, if you have P equal to R2 and simply look at this, and you take the canonical trivialization that I mentioned, this one, theta, then chi is just psi2. And this form unfortunately, is not the matrix we considered before. So where is it? This matrix. It will be minus this matrix. So the transpose of this matrix. And this is the reason why the usual Vaserstein symbol is not the generalized Waserstein symbol associated to theta, but to minus theta. So that's the reason. So up to this choice of the trivialization, the definitions coincide, and up to this isomorphism. Yeah. Okay, that's one remark, and then the criterion. So we'll be more technical now. So I define Pn for n at least 3. Simply take the direct sum of P and R to the n minus 2. And consider this element En, where all the coordinates are 0 and the last one is 1. I will always discuss the special case when P is free, because that's easier to digest maybe. So R is a unitarian ring of dimension at most 4. This was the case in my question at the beginning of the talk. Now we have to assume some cancellation property. So SLP5 acts transitively on P5, which is a technical assumption to make this theorem true. Yeah, you can ignore that. So under reasonable assumptions, actually quite reasonable, this assumption, under reasonable assumptions, this orbit space is trivial if and only if this group V tilde SL of R is trivial and some further condition is satisfied. So E4 is this element for n equal to 4. And you can simply apply all these automorphisms of determinant 1 on the left-hand side and get new elements. And this set of elements should be equal to the set of elements if we take the subgroup by generated by symplectic automorphism. So symplectic with respect to this alternating form. Okay, that's quite technical. Maybe it's instructive to look at the case when P is R2 to get some illustration. So in this case, this first assumption is just SL5 acts transitively on the set of unimodular rows of length 5. And this orbit space is then trivial if and only if this group is trivial, as before. And SLP4, I mean P4 in case P is free is just R4. So we can identify this with SL4. And this will just be, if we take the usual trivialization, will just be psi4. So this will just be the symplectic group, SP4. And these orbits will be the same, where R4 is the column vector of this form. That's what this theorem says. Okay, that's a general criterion for unitarian rings. That's why so much technical assumptions are in the theorem.
Eric, may I ask you?
Yeah.
Is this V tilde easier to understand or compute than the unimodular modular SL?
Sorry, I didn't hear you.
So in the second statement, you have a criterion for unimodular modular SL of R being trivial if this V tilde SL of R is trivial and something else. So
Yes.
is this V tilde SL simpler to compute?
Definitely more computable, yes.
Okay,
quite computable. Using the Gersten-Grodnik-Witt spectral sequence, one can compute it. It's as computable as one might hope. So it's a Hermitian K-theory group. Yeah, so this is the nice part. The annoying part is this assumption. And now in case we deal with smooth affine algebras over algebraically closed fields of dimension 4, one can actually prove that this assumption is simply true, this second assumption. So this is actually now the proof, the main proof that I want to discuss. Actually, I already running out of time, to be honest. This assumption is simply true. If D is divisible by 4, and R is a smooth affine algebra of dimension D, of an algebraically closed fields with D factorial, then these orbits are the same. And I'm trying to save some time. So up to transposition, it's just a statement about unimodular rows. Now here, ED is on the right, but if we take the transpose of this equation, we simply have to prove that these orbits of unimodular rows are the same, some technicality. And Vaserstein already proved that this orbit space is trivial, and hence SLD acts transitively on the set of unimodular rows. So all we have to prove is that SPD, where is it here, also acts transitively on the set of unimodular rows. So we can simply pick one. So we pick this one, 1, 0, 0, and so on. And we want to prove that every unimodular row is the first row is in the orbit of pi. So is the first row of a symplectic matrix. And the idea is to somehow reduce it. So assume phi A. We have found phi A. Phi A is a completion. So A is a unimodular row, and phi A is a completion. And assume that phi A is in the image of the forgetful map from symplectic K1 to K1. That's just an assumption. That's a reduction step number 1. Then we get by stability results that any matrix in SP is already generated by SPD. That's just by dimension assumption. So phi A is actually equal to psi for some psi in SPD in K1. So they are the difference is stably elementary, but in fact, this K1 stability result implies that they're already this difference is already elementary. So we can actually show by this well-known theorem, it was proven by Vaserstein in the 70s, I think. These orbits are always the same. So there's tau, because this is elementary, there's tau, this is elementary. So there's tau, which is elementary symplectic, such that pi tau is pi phi A psi inverse. And simply multiplying this equation by psi on the right, we get that A, which was pi phi A, is pi tau psi. And tau psi is symplectic because tau is elementary symplectic and psi is symplectic. Okay, so this is a reduction step. All we have to do is to find phi A, which is a completion of this unimodular row, and whose class is in the image of the forgetful map from symplectic K theory, symplectic K1 to algebraic K1. Okay, that's the first reduction step. So we have to find phi A as above. The second one concerns the row. We don't have to find phi A for any row A. We only have to find phi A for certain types of rows. So Vaserstein proved that any unimodular row can be transformed by elementary matrices to such rows where the last coefficient is a power, a d-1 factorial fold power. And now again, we use that elementary orbits are equal to elementary symplectic orbits. That's just well known. And then in fact, we know that A can be transformed via elementary symplectic matrices to this row B prime. And hence, because they're in the same symplectic orbit, we only have to find phi B prime for rows of this form. So where the last coefficient is a power, a d-1 factorial fold power. And now the idea is to use Suslin matrices. So hopefully not too quick. Okay. How much time do I have left?
7 minutes. But
Can
we
you
will
give me?
if you take 10.
Okay, I'm trying to speak quickly. Yeah. Okay. So yeah, you use basically Suslin matrices to get this phi B prime. Maybe this is the point where I maybe shorten the talk a little bit. So essentially, you use this Karoubi periodicity sequence. So you have Suslin matrix construction gives you an invertible matrix SD called Suslin matrix associated to B this row, and some section, which is of rank 2, d-1, and a completion phi b prime, which is called phi b prime for a reason. That will be phi b prime, the matrix that we are looking for, which is a completion of b prime. And the class of phi b prime in SK1 is equal to the class of the Seussian matrix. And then well, I'm trying to shorten this. So we would like to show, left to prove, is that the Seussian matrix, or equivalently this class of phi b prime, is in this image of the forgetful map, as I wanted to show. And we use this Karoubi periodicity sequence. So the image, this sequence is exact. So that's a hyperbolic homomorphism defined by this equation, but it's actually irrelevant how we define it. So the image of this map is simply the kernel of this map. So I'm going to abbreviate this. So we find, as one can show, this Seussian matrix is actually in the kernel of this map. So I'm basically, yeah, leaving out these slides, maybe just to talk about the generalized Serre question. So you basically show that this Seussian matrix is in this kernel, and with some work, with some, yeah, universal space, yeah, representing unimodular rows and so on. But let's not do that to save some time. And I should mention that the same result is true if D is 2 modulo 4. This was proven by Anyan Gupta in 2015 using similar methods, but the proof was a little bit easier because he used SD when D is 2 modulo 4. So the Seussian matrix is automatically in this image. There is nothing to show basically. Whereas in the case when D is divisible by 4, we really have to compute something. So this is the 2 slides that I left out. Okay, sorry. Yeah, so the same statement is true. SPD acts transitively on the set of unimodular rows of length D. Now, what do we get? What can we deduce from this? The general criterion. So let R be a smooth affine algebra of dimension 4 of an algebraically closed field with some characteristic assumptions. 6 is a unit. Then all stably free R modules of rank 2 are free if and only if this group V tilde SL is trivial. So basically the cancellation property of stably free modules or of the free module of rank 2 can be computed using this group, this Hermitian K-theory group. Okay, so yeah, very shortly the proof, you use Seussian's cancellation theorem to show that any stably free module Q lies in the fiber of the stabilization map phi 2. Then you have to show that this fiber of the stabilization map is trivial. So 3R modulo GL3R is trivial, but it's equivalent to this triviality of this quotient. Just multiply, if you have a matrix which is a completion, just multiply some row with the inverse of the determinant, and you see that this is equivalent. It's very easy. And by the previous theorem, we know that this orbit space is trivial if and only if this group is trivial. So that's an easy corollary of the general criterion of unitarian rings and the theorem on the symplectic group that I proved just 1 minute ago. Okay, so this is the general criterion for stably free modules of rank 2 to be free. Okay. Some further questions that I'm not going to address too much now. We don't know if the vanishing of this group is really enough for a general projective module of rank 2, because we, as I showed you a few minutes ago, this criterion that I proved has this annoying second assumption, and we don't know if we can drop it for general P. For the free module of rank 2, we can drop it. That's what this theorem on SPD was all about. And we don't know yet if the generalized Waserstein symbol is in fact a bijection. We just know that this orbit space is trivial if and only if this orbit space is trivial, but we don't know, in case P is free, but we don't know if it's actually a bijection. It's definitely a surjection, but not yet a bijection. But this is maybe something for the future. Okay, There are some further theorems that I'm not going to address so much now because I don't have much time. So one can prove that the generalized Waserstein symbol on this orbit, defined on this orbit space, is actually a bijection. That's the analog of the result by Rao van der Kallen, and one can actually give a new proof of the cancellation theorem of Asok-Fasel, in a way a purely algebraic proof of the theorem by Asok-Fasel, which was proven by using motivic homotopy theory. That's this result, and basically mimicking the proof of Fasel for the case when P is free. And then a fairly new cancellation theorem for rank 3 bundles over smooth affine fourfolds over algebraically closed fields. So if all the Chern classes are trivial, then projective module of rank 3 is already cancellative. Okay, but this is actually not the main part. So now towards the end, maybe 5 minutes. The generalized Serre question. So as you might know, so when K is a field which admits an embedding into the complex numbers, we may associate it to any smooth K variety, a complex manifold, and this assignment can actually be extended to a functor from the unstable motivic homotopy category to the homotopy category of topological spaces. And a smooth K variety is called topologically contractible if this associated complex manifold is as a contractible topological space for any such embedding from K to the complex numbers. Okay, so that's the notion of a topologically contractible K variety. Now, Serre asked the following question in 1955: if K is a field, are all algebraic vector bundles on the affine space trivial? And this was, as you might know, solved by Quillen and Suslin independently in 1976. So all algebraic vector bundles on the affine space are trivial, or in other words, projective modules, finitely generated projective modules over polynomial rings over fields are trivial. Okay, now the generalized Serre question is the following: if X is a topologically contractible smooth affine complex variety, then are all algebraic vector bundles on X trivial? This is of course motivated by Serre's original question, because the affine space is the primordial example of a topologically contractible smooth variety. And some results. So first of all, one can use Serre splitting result. Any projective module of constant rank is a direct sum of this form where P is of rank D. So we can basically always focus on projective modules whose rank is at most the dimension of the ring. That's just Serre's splitting theorem. And then Goya proved in 1980 that Chow1 of a topologically contractible smooth affine complex variety is trivial, which basically solves the generalized Serre question in dimension 1 because of Serre's splitting theorem. We only have to, if we have a topologically contractible smooth affine complex variety of dimension 1, we only have to prove that line bundles are trivial, but this is exactly what this theorem says, without any assumption on the dimension, by the way. But for lines, for topologically contractible varieties of dimension 1, this solves the question. And similarly, in dimension 2, so Goya-Shastri proved that in 1989 that Chow2 is trivial for any topologically contractible smooth affine complex variety of dimension 2. So for any surface, complex surface, which is topologically contractible. And therefore, because vector bundles are completely classified, as I here indicate here, completely classified by Chow groups, the generalized Serre question has a positive answer in dimension 2. And in dimension 3, I'm trying to be quick now, the topologically contractible, if you have a topologically contractible complex variety of dimension 3, then all algebraic vector bundles are trivial if and only if Chow2 and Chow3 are trivial, simply because vector bundles are completely classified in terms of Chow groups. So all these Chern class maps are bijections. The first one is a result by Asok-Fasel that I mentioned earlier, and this rank 3 case was proven by Kumar-Murthy in 1982. And this not solves, but gives at least a very sufficient and necessary criterion in dimension 3. And now using my result on cancellation of rank 2 bundles, one can prove that in dimension 4, without any assumption, so not topologically contractible, just a smooth affine variety of dimension 4 of an algebraically closed field, that all algebraic vector bundles are trivial if all the Chow groups are trivial and if this cohomology group vanishes. Why is that? Well, if all the Chow groups are trivial, it's well known that using Riemann-Roch without denominators, that reduced K0 is trivial, and well, Chow 1 is trivial, so line bundles are trivial. And because of this exact sequence, it follows that by the triviality of this group, that all vector bundles are stably trivial. So it's reduced to cancellation questions. Now, Fasel-Rao-Swan and Suzin's cancellation theorems imply immediately that V3 and V4 are trivial. And now it's basically only left to prove that V2 is trivial. But these vanishing assumptions imply, using the Gersten-Grodnik-Witt spectral sequence, as I told you before, that this group V tilde SL is in fact trivial. So by the general criterion I gave on the cancellation of projective modules of rank 2 or free modules of rank 2, this implies that V2 is in fact trivial. So this is a very general statement, and as an immediate corollary, that's the last slide. As immediate corollary, we get a criterion for topologically contractible smooth affine complex varieties of a dimension 4, namely all algebraic vector bundles are trivial if, that's only a sufficient criterion, by the way, if the Chow groups are trivial for 2, 3, and 4, Chow I for I equal to 2, 3, 4, because Chow 1 is trivial anyway, by Goya's result, and this cohomology vanishes. This H2 of X with values in the third power of the fundamental ideal sheaf. Okay, that's the criterion for topologically contractible varieties, smooth affine complex varieties. Now there's a conjecture by Ashok-Östwehr asserting that if X is a topologically contractible smooth affine complex variety, and if we choose a base point, then there should at least be an integer, a non-negative integer, such that the n-fold P1 suspension should be A1 contractible. So that's just a conjecture, motivated by some results of Ashok and the motivic conservativity conjecture. And now, if this conjecture holds, that's the last remark I want to give for this talk. If this conjecture holds, then this would automatically yield an affirmative answer to the generalized Serre question on algebraic vector bundles in dimension 3 and 4. Because in dimension 3, everything is determined by Chow groups, and in dimension 4 by Chow groups and this cohomology group. But yeah, because of this conjecture, all these groups would actually be trivial, and hence the generalized Serre question would have a positive answer in dimension 3 and 4. So that's the last application I wanted to mention. So thank you all for your attention, and if you have questions, just ask.
Thank you. Questions time.
So I have a question. If
Yes.
it's about this Vaserstein symbol that you described. So this seems to be mapping from some something that looks kind of like a Grassmannian, like connected components of a certain, or a Grassmannian or something like that, to a Hermitian K-theory group. So can we think of these results as some kind of connectivity bound from maps from Grassmannians to Hermitian K-theory spaces? Is the
Well, you can define the usual Vaserstein symbol as there's a universal Vaserstein symbol from, well, maybe just go back. So we have this map. This can be universally defined as a morphism, for instance, if we take smooth affine schemes over a base field in the motivic homotopy theory, unstable motivic homotopy theory. So just you have a morphism from A3 without 0, -0, to what's it? Schlichting Triparty implies it's
Yeah.
SL modulo SP. So you can define it by means of a morphism in the unstable A1 homotopy category from A3 without a -0 to SL modulo SP. So that's maybe the closest I can tell you, the closest I can come to your answer. Apart from that, probably over more general base schemes, you can do something similar for the generalized Waserstein symbol, but I'm not too sure.
Okay, thank you.
Are there more questions? Well, Tariq gave us a lot of information to overthink and lots of facts. I personally like these splitting questions a lot, so I'll look more into your work. Thank you.
So the most important, most interesting question for me is actually this last part here. So if anyone knows something about it or wants to work on this, I would be very interested to learn more about the subject actually.
Well, this seems like a super complicated conjecture.
Yeah.
So this is stronger than conservativity conjecture as far as I understand.
This is stronger because yeah, it concerns the integral motive, not just the rational motive.
Yeah.
Because there are some results by Asok. I think in dimension 2, he proves that if a variety is set acyclic, so its complex realization has only trivial homology, singular homology, then the motive is already the integral motive is already trivial, and hence this topologically contractible variety is already stably contractible. So yeah, it's motivated by this. Yeah. So it actually proves already that on stably contractible varieties, all vector bundles are trivial in dimension 4. For instance, it's another application. And this is, of course, very easy for A1 contractible varieties because of the representability result by Asok, Oyoa, Wendt. But for stably contractible varieties, it's actually a bit surprising, for me, to me at least, that in dimension 4, or at most 4, so dimension 1, 2, 3, 4, if a variety is stably contractible over the complex numbers, then, or actually over algebraically closed fields, then all vector bundles are trivial.
So do you know which example I should keep in mind for a stably contractible variety which is not A1 contractible?
For instance, I think Adrien Dubolo, Sabrina Pauli, and Paul-Arne Östwehr construct such fourfolds in their paper on affine modifications, if I'm not completely mistaken. There are some examples, and Asok proves some, constructs some, basically affine modifications is the key to many examples for such varieties. So Asok proves in his paper on acyclic varieties that the affine modifications give rise to many such examples. So there are many examples who actually, which actually suggest that this conjecture is true, but yeah, one doesn't really know if it's true. It's probably very hard to prove this.
Seems so if we watch Ayub long enough. More questions? Okay, let's thank Tariq again. And then, okay, after. So let's take a break. And the next talk is in 15 minutes. There will be a talk by Akil Matthew. So